3.1 problems. Number one, we're going to find K. They're going to say equilibrium constant. Of course, all the time. They're not going to actually say K. So we're going to find the expression for it, though. This time we're going to write it out. And of course, it's products over reactants to the power of the number in front. And that is this. This 3 becomes that exponent. That 2 becomes that exponent, etc. Now for part B, what they did is they multiplied everything by a half. So that's not 2, that's 1. That's not 3, that's 3.5, 1.5. So what you do is you take the multiplier and use it as the exponent. Because essentially what you have is, instead of having square, or let's say the third power, you have taken, then you multiplied this by a half. You got 3 times a half, which means this exponent is 3 times a half. So it's the previous amount, the cubed part, to the power of 1/2, which is the square root. So it's the square root of the previous amount, but that's going to be true in all cases. It's going to be the square root. So you can just skip all this in practical terms on the test and take the previous value, whatever it is, to tell you, let's say they said it was 16, and you can say, oh, the new value will be square root of 16, it'll be 4. So you can just take the old value and just say it's square root of that previous value. In part C, what they did is turn everything around, and now the products are the reactants are the products, which means that this flips. This is the inverse of that, which means you get the inverse of the answer, or you get 1 over the previous value. Notice that this is mathematically the same thing as this. I like to write it this way to remind myself I don't miss a -1 or something. Technically, they're right, but I don't find it as useful. On 2, we're being asked to find an actual value for the equilibrium constant K, and they give us these values. So notice all the coefficients are 1, so all the exponents are 1, and we're going to put them in. And you don't get a calculator, but hopefully we learn to cancel things in like 6th grade. So this is a half, which means it cancels out this, and I get 1 over 2.5. Now they really do think that you're going to be able to manipulate some decimals, and now you could do 1 into 2.5 and drive yourself bananas doing long division, but let's not do that. Let's say, well, I know what this is similar to. It's an analog of this. I know what 1 over a quarter is. 1 over 1/4 is 4. How many quarters can you shove into 1? The answer is 4. Except now this is where it gets tricky, and I have fooled myself before. I moved this decimal 1 spot smaller. So when I divide by a smaller number, my answer gets too big. This answer is too big. And it's tempting to get this backwards, and I've done it, because you say, oh, I moved it smaller, therefore my answer is too small, right? That I moved this decimal smaller. But no, when you divide by a smaller answer, you get a bigger answer. This answer is too big by 1 decimal point. So move it back, and the answer is 0.4. On 3, it might be a little bit tough to realize where we're going to go with this. So give that a read, maybe a couple times. What is the question? It's calculate the partial pressure of the chlorine atoms, which is this, because that's a covalently bonded molecule. And plus, it tells you the chlorine molecules, it gives us a value, right? What are we looking for? The partial pressure. Another giant clue. This is in atmospheres. That's in pressure. We're looking for pressure of the chlorine atom. So what we would do is set up a Kp expression like this. This would be the unknown because that's the atoms, and also notice that gets squared because of that 2 there. And I have a value of this, it's 1.5. The trouble is that as it stands with the information just given right here, I have 2 unknowns, because here's the unknown that I want to solve for. Essentially, that's x, but I don't have Kp. I'm going to have to go chase down my value for Kp so that I can have only 1 unknown in this equation here. We do have a way to get there, of course. There must be some way, right? Well, it's that this equation relates Kp to Kc. And they told us Kc, so that's your other big clue. So we know Kc, and we flip to the back of back to the front of the booklet. Can you go back to the front? I guess you can. And we find the equation, and we know R, and get the right R. Please get the right R. Don't get the one that involves joules or torr or something. And they told us the temperature, which we convert to Kelvin. Don't forget to convert to Kelvin. None of this stuff works with Celsius, right? Only that Q equals mc delta T it can work with Celsius, and that's because it's delta T is change in temperature. But if you need a raw figure for a temperature, it's got to be Kelvin. So add the 273 on there, and now we have the KC value they gave us, R from the booklet, and we added 273 to the temperature. And by multiplying, excuse me, and we can take delta N. Delta N is the change in moles of gas, because delta's change and small n stands for moles for reasons unknown. I was never told. So this goes from 1 mole of gas on the left to 2 moles. So that's a gain of 1. So delta N is 1. 2 minus 1 is positive 1, which effectively kind of disappears because the positive 1 is kind of pointless. So we can just take this times this times this, and we have Kp. It's 148. Now I have something that I can solve. I have 148 equals x over 1.5, and just multiply and square root, and we get the partial pressure of the Cl atoms. Give for a real thorough read, because this has got some real trickery to it. I kind of admire this problem for how complex it gets. So we've got a certain number of moles in this 2-liter vessel, right? And we know we're starting with this, and we got to find out what it's ending with. Calculate the concentration of all three at equilibrium. So that's what it's going to settle to. That at the end of all this is going to be at equilibrium. So we're going to introduce the idea of an ice box here: initial concentration, change, and equilibrium, and we're going to put in molarities for these values. Now, that means that we're going to have to recognize that it's a 2-liter vessel. 2-liter vessel, so we're going to divide everything by 2. Now, for you extra math nerds out there, you know, people after my own heart in a certain way, you might recognize that if we divide everything by 2, there's no mathematical point. And you can go back and you can try it yourself, and you can get away with it this time because everything's in the same vessel. And I actually did it just to double check myself. But how about we not get into that too deep right now, because that is playing fast and loose with the math, and in the heat of a test and the pressure of the moment, you may mess that up. So I'm going to recommend that we just take the moles and divide by 2, and we put in the molarities here as our starting amounts. However, which way is this reaction going to go? And you might think, what do you mean which way is it going to go? It's at equilibrium. But you know what? No, it's not. And they never said it was, and that is the trick to this. They never said it was at equilibrium. They said they put this in, and it is allowed to reach equilibrium. So do these amounts represent the molarity at equilibrium? What if they don't? I mean, what's the likelihood that it does? What's the likelihood that they planned that far ahead? What if they didn't? And well, they didn't. So what we're going to do is use the concept of Q, which stands for quotient or dividing answer, and we're going to take the mathematical tool of K and use it, but with amounts that do not represent equilibrium state necessarily. So we're going to take products over reactants to the power of the number in front. So we're going to take these values here, right? And products over reactants to the power of the number in front. We're going to punch that in the calculator and get a value. So what's the K math give us with these molarities? Well, it gives us 2.25. What is K though? What is K? They tell us that K is 0.02. So this is much greater. This is over 2, and the other one is 0.02. This is over 100 times greater. It's much greater than K. So Q represents the ratio of the products and reactants as it stands when they were put into the vessel. Is that the amounts that they would be at equilibrium? No, Q is way too large. It's much too large to be K, but however, it will reach equilibrium. It is allowed to reach equilibrium. At equilibrium, this value will be true. So what has to happen for Q to reach K? It has to get smaller, because when it reaches equilibrium, it will be 0.02. So what does that mean for the chemicals? If Q is too big, you have too much numerator by proportion, don't you? If you had less numerator, you would have gotten a smaller answer. And that's what's going to happen, is that this is going to decrease and these are going to increase until K is true. So which way is this system going to shift? we just said we're going to get less HI. We're going to get more of the other two on the bottom, more of the other reactants until Q is true. So this reaction is going to shift left. And that's really key here, and that is not skippable, because when we write this icebox out, we put in these starting values, remember half of this and half of that and so forth, it's going to run left. And what we're going to do is lose HI, because we're going to effectively make this the reactant and these are the products. And there is a reason that they didn't turn this around. So I wouldn't really recommend doing that. I mean, you can get away with it, which I can explain, but I would leave it like this. Just say, this is going to run left. And if it's going to run left, we're going to destroy some of this and make some of these. So we can make an unknown amount of this. I mean, we will make an unknown amount and the same unknown amount, because one of these and one of these are produced at the same time. But we will destroy two of these every time that happens. So we'll make some unknown amount, the same unknown amount, and we will destroy double whatever that amount is as this flows to the left to reach equilibrium. Well, since we started with this and changed it this much, these are the amounts at equilibrium. The reason that they didn't turn it around is because if you flip this end to end, we just talked about back over here, that if you flip the reaction end to end, the K value becomes the inverse. So you can flip it around end to end, and you can put, HI first, arrows, and so forth, but then you have to remember to use the inverse of K. And it's a toss-up. Is it harder to remember to subtract out of here, or is it harder to remember to use the inverse of K? Well, they chose to write it the same way so that they could keep the value of K. So here's the products. They're the right side over reactants, the left side. The way it's written, these are the reactants and that's the product. And I know that it's running left, but it's also possible to say it's right side over left side. So the right side to the power of the number in front over the left side to the power of the numbers in front equals the stated value of K. So we take this value for HI and we put it in the numerator, and it's squared because of the coefficient here. And these two become multiplied by each other, both to the power of 1 in the denominator. And what we end up with here is a sort of a tight squeeze where it looks like we're going to have to use the quadratic formula, but we're going to wriggle out. And on the real test, they would never ask the quadratic formula, partly because it's a big waste of time, and also people would just program it into their calculators to get out of the waste of time. And so it wouldn't even be a test of skill anyway. But we're going to wriggle out because we've got a squared term over a squared term, and we can square root both sides. Now square root of this, and then we can square root this and cross out that. So there's only one of these, and square root the bottom, so we cross out one of these, and then we have some algebra that's kind of back down to 8th grade level, and we can solve for x. So having solved for x, make sure that you don't just say that that's the answer, because the question was, what are the values of the concentrations of these at equilibrium? And remember, it's these numbers plus or subtracted out of x that are the final amounts. So x is not the final answer. Go put x back into these amounts here.